you don't have other numbers to check at this step. Next step, you have some special factors which are, how to say, they are less interesting than previous factors, but you can do a very quick check for these factors. In base 10, you have 9 and 11, which are special factors to test. These factors, you know how to do it. To check for 9, you just have to sum all the figures, and until you have only one figure on the result. On this sample, I take number 1, 2, 3, 4, 5, 6, 7, which is summed like 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7, which gives 28, which is 2 plus 8, which gives 10, which is 1 plus 0, which is 1. 1 is not 9, so it is not a factor of 9. But 9 is not a primary factor, a primary number. 9 is a multiple of 3. So if the result, my result was 1, if it was 3 or 6, 3 would be the factor of the number. So it's quite easy to check and really quicker than doing division for 9 and for 3. For 11, the same principle apply. For my number, it is changed to 1 plus 23 plus 45 plus 67, which gives 136, which gives 1 plus 36, 36, which gives 37. To check for a factor like 11, in fact, you have to search for the 2 digits of the result must be the same. If the result was 33, or 11 would be a factor of the number. So it's the same, you have only addition to do to check a number. No need to do a division. And in our case, in base 10, we can do all the calculating only once, because if you do for 11 in first, you can reuse the 47, which is the result, to calculate for factor 9, and you check for factor 11, 9, and 3.
Very efficient.
In base 2, the same principle apply, but it's really more interesting, because by using some powers of 2, you can check for factor 3, 5, 7, 11, 13, 17, and if you really want, 19. It's every time the same principle which is used in base 10 and in base 2. And this is really efficient with big numbers. So, about the classical algorithm, you can always find methods to not check a part of the divisors, but there is always a lot of calculation remaining. And another problem is that the amount of calculation for a division is proportional to the square of the size of the number used. It grows like a multiplication. A division is an efficient way to reverse a multiplication for a given single factor. But in our case, it is not very efficient because we just care about the fact that the rest is 0 or not. We don't care about the main result of a division. So there is a lot of waste in this calculating. And one thing is that a compound number is the result of a multiplication. So a division for every factor is to check. A division for every factor to check is a lot of work for a little result. All we care of is that the rest of each division is 0 or not. And all the calculation for the division is lost after the division. The last problem is complexity of division, which squares with the size of the number. When the number size double, the amount of calculation is multiplied by 4. So, after a lot of thinking, I devised a new algorithm with these remarks. In a multiplication, the x figures to the right of a number are fully defined by the same x figures from the two numbers on the top of the multiplication. The calculation for a given right part can be reused for all divisors for all divisors with that same part on the right.
So you mean like 1, 2, 3 and 2, 2, 3?
Sorry?
So you mean, for example, if it's a long number that ended in 1, 2, 3, you could also use it to check 2, 2, 3?
No, I think it means that if it ends in 1, 2, 3, and he figures the result, then that result will apply to all numbers.
Yes, okay.
You will see, I will show you a program which shows the system. So, for a given number, you check first for the special factors, and after you launch your algorithm. This is how my algorithm functions. For a given figure, you choose a pair of figures p and n, such as the same given figure of p multiplied by n match the same figure on the number two factories. It can look a little confused, but you will see in the problem just after. And if in number 1 I found a pair which match the number I am looking for, I am going to step 2, which is move to the next figure. In step 3, if you did not find a factor after looking at the next figure, you have to choose another pair p and n, and repeat stage 2. If there is no more pair to choose, you have to backtrack. I will show you an example of program which use ubasic. Ubasic is a basic which can compute with integers of 2,600 digits without losing anything. So here is another program that I use to show the algorithm. I enter a number and I launch the calculating. The unit was 7, and you see that, you may see. Can we adjust the light of the, because we don't see a lot of things. Do you see?
Yeah.
Yes? I was looking for number 1, 2, 3, 4, 5, 6, 7, and the program have chosen the third pair, which is 1 and 7, which match the first figure. After that, the program will look for the next figure and it choose 0 and 6 to match the next figure, and so on. Here you have a match, because one is the factor of every number, but we are not interested in this one, so I continue. You see that the program has do some backtrack, and now is running.
What is it looking for?
He wants to factorize the number 1, 2, 3, 4, 5, 6, 7.
No, I understand, but what is like the iteration? What is it? I don't understand.
What's the test that you're doing? So you're multiplying which number times which number in
I think he's multiplying the two top numbers, 1001 times 1567. And the key is, you realize that the only way that you can get the 7 in the ones place is for the two rightmost digits to be 1 and 7. It's the only way you can help.
No.
So then he moves on to the next digit.
It's the first peak.
I'm sorry?
The 1 and 7 is the first try.
Okay, so that's the first choice.
Because to have 7, you can have 3 and 9.
3 and 9. Right. So but he's trying each of those possibilities in turn, and then moving forward to try to find the factors. Is that right?
Yes.